following theorem, Schroder-Bernstein theorem. So before we write explicitly what the theorem says, so it is basically about how we can conclude that two sets have the same cardinality, right? So let us consider the following situation. Suppose we have two sets A and B such that we have a map F where F injective. Okay. Then inside here we have the image of F and the image of A under F. So this is F of A. Okay. So now if we restrict the map F not from A to B but from A to F of A, then we have bijections from A to F of A. So this is bijection, right? So since, remember that if we have a bijection, that then the cardinality of the two sets are same, right? So then, because of this bijection, the cardinality of F of A is equal to the cardinality of A. So in that sense, then we can see that we have a kind of copy of A inside B. Okay? So in that sense, then we can say that since A is living inside B, then the cardinality of A must be less or equal to the cardinality of B, right? And that's exactly what the theorem says. If there exists F from A to B and G from B to A, where both of them are injective, injective maps, then the cardinality of A is the same as the cardinality of B, and the cardinality of A is the same as the cardinality of B. So if we have this F, then we can see that we have a kind of a copy of A inside B. So then the cardinality of B must be bigger than the cardinality of A. And by using the G, similarly, we can have a copy of B living inside of A. So again, our intuition tells that it means that B is kind of part of A, so the cardinality of B must be less or equal to the cardinality of A, right? So that's what the theorem says. But if we want to refer to the original definition of when two sets have the same cardinality, which is that if we have a bijective map, so in order to prove this, somehow we need to create a bijective map between A and B by using the information that F and G are injective, right? So that is the idea. So let me repeat again. In order to prove this, we need to find bijection from A to B, right? So let's call it H. Let's think about how to use the map F and G. Okay, we do some wishful thinking. So let's suppose that we can split A into two sets. Let's say this is U, okay, and then we have F of U. then the remaining part here is a minus u, and the remaining part here is b minus f. Okay. By using the map f, we can map every element in u bijectively to fu. Right. Now how about the remaining? So we need to somehow use the map G, right? So if it happens that G of this thing is equal to let me see. So we have, oh, actually, not what I want to say. I want to map this to, I'm sorry, let me leave it again. So I want to map the remaining by f here. This is b, and this is f of a minus u. And this is b minus f of a minus u, right? So we can map bijectively all elements in a minus u, and then we wish that we can also do the same, map all elements in this remaining part bijectively to u, okay? But in order to do that, then we need to have g of this thing needs to be equal to u. So we need g of b minus f a minus u is equal to u. Okay, so then what we need to have is we need to split this a into u and the remaining part, where the u have a certain property, namely that we are looking for the set u such that this map, the image of this thing under G is equal to u. Okay, so once we have this, then we can bijectively map each element in here to u, or we can reverse by using the G inverse. We can map every element of u to here and every element of a minus u to here. Hence we have a bijection. Okay, so then the problem is reduced to finding the set u such that this statement is true. Okay, now in order to find this particular u, we need a lemma. And the lemma is called the Knaster-Tarski lemma. Knaster-Tarski fixed point. Yeah. The lemma is of Knaster-Tarski fixed point. So the lemma says that let C be a map from a power set of x to itself. So this P of x indicates the collection of all subsets of x, right? Be monotonic. What does it mean? i.e., for all a subset of B in Px, we have P of A is contained in P of B. So this is what monotonic means. Okay, when there exists Z in Px such that Z is a fixed point under phi, namely phi of Z is equal to Z itself. Okay. So first we're going to prove this result. Proof. First, we will collect all subset of X, say Y in the X, such that Y is contained in phi Y. Okay. Notice that this collection is non-empty, because at least it contains one element, namely which set? Namely the empty set. So empty set is in C, hence C is not empty, right? Next step is we will collect all elements of C. So we will collect all the image of all elements of C. So let Z, so define Z, combine all of phi Y, where Y is coming from C. Okay. Now let's take a look. What do we have here? So take Y and C. Okay. Then certainly, because then phi Y, sorry, by definition of elements of C, if we take an element in C, then we have Y is contained in phi Y, and Y is contained in phi Y. Right. Also, phi Y is contained in C. Why is that? Because remember that this phi Y is one of the set that of this type. Meanwhile, here we combine all kind sets that in this form, right? So then phi Y is contained in Z. So if we combine Y contained in phi Y and phi Y contained in Z, therefore we have that Y is contained in Z. Now comes the monotonic part. Since phi is monotonic, and phi is monotone, then we have phi Y is contained in phi Z. Right? Okay, so let's continue. So again, since phi is monotone, then phi Y is contained in phi Z. But this is true for all Y in C. Since this is true for all Y in C, thus if we take the union of phi Y, where Y is coming from C, then it is still contained in Z. Why is that? Because each of these things is contained in phi Z. So if we take the union, it's still contained in phi Z. But this is exactly Z by definition. Okay. So then we have Z is contained in phi Z. So it means what? It means Z is an element of C. So the other way around, we would like to show that phi z is contained in Z, right? So why is phi of Z contained in Z? Okay, so from here, then Z is element of C. This implies that Z is just part of this union of all phi y, where y is coming from C. Because when y is exactly Z, then we have phi of Z is one of the set that we combine here. So clearly then phi of Z is contained in this. This is Z. So Z is contained in phi of Z, and phi of Z is contained in Z. Therefore, phi of Z is exactly equal to Z. So we just proved the Knaster-Tarski lemma. Yeah. Okay, now we are ready to prove that, remember that our objective is to find a set U such that G of f a minus u equals to U, right? If we have this kind of U, which is a subset of A, then we are done. We can prove the Schroder-Bernstein theorem. Okay, this is our objective. Okay, so we claim that this U can be obtained by using the fixed point lemma. So consider the map P from the power set of A to itself. Okay. For any given x here, we will map it to f a minus x and then take the g. Okay. So let's see that whether this expression is indeed a subset of P of A. So when we have an x, then A minus x is a subset of A, and the image under F is the subset of B. Since G is a map from B to A, then G of this thing is a subset of A. G of this thing is a subset of A. So this is a well-defined element of P of A. Okay. So now remember that our objective to show that for a certain U, this map G of f a minus u is equal to U. Namely that we are looking for U such that phi of U is equal to U. Remember that we want that this thing is equal to x itself, right? Or in other words, we are looking for a fixed point of phi, right? And according to the lemma, to show that there is a fixed point, it is enough to show that this map is monotone. Okay? It's enough to show that phi is monotone. Okay? So take x subset of y, where both of them are from P of A. Okay? Since x is contained in y, please allow me to use this notation, although I don't like it that much. If I write on paper. So let's see. So since this is contained in that, then if we minus a by y, it will be smaller when a is minus by x, right? And the next one, since this is a subset of that, then the image of this guy under f will be smaller than the image of this. So f of a minus y is contained in f of a minus x. Okay. Now both of them are subsets of b. And b minus f a minus x will be smaller than b minus f a minus y. Okay. Alright. Now we use the G-map from B to A. These two are subsets of B, and hence G of this thing is smaller than G of the right hand side. But this is the definition of phi of x. So phi of x is contained in phi of y, i.e. phi is monotone. Then we are done. According to the lemma, we can justify that there is a subset u of a such that phi of u is equal to u, which then, I'm sorry, this one is, we missed this b minus, okay. Alright. Okay, let me recall again what we need to do now in order to get a bijection from A to B. So the bijection is as follows. First, let U such that subject of A such that the U is such that U is the fixed point of phi, which means that G of B minus f of x minus a minus u is equal to u. Okay. So then we have the set A here and the set B over here. We have the set u and a minus u. Here we have f of a minus u, and here we have b minus f of a minus u. Okay. Now by using the injective map f, we can have a bijection from a minus u to f a minus u. Okay. And then since this u is exactly the image of this under G, because G of this thing is equal to u, then the G map is also a bijection between this set and that set. Okay, so this is F, this is T. So then, in order to create an explicit map, an explicit bijection from A to B, we can just define h of x is equal to f of x if x is in a minus u, and then if x is here, then we just reverse the g. It will be g inverse x if x is in u. Okay, and we are done. So thank you very much for watching. See you again in the next video.